but it could risk, you know, my job and all. So we don't want to do that. So there we go. So now I'll be nice. And like I said, I will keep coming back to this screen. If I'm going to add something to it, great. And I'm going to go in order, starting with mechanics. That means orbits and gravitation first. We good to go? All right.
Did you add momentum to the list?
I would be happy to go and add momentum to the list. When you say momentum, that's a pretty big topic. Do you have a focus or just go over momentum? Angular, linear, collisions, whatever?
Not so much collisions, but like angular and linear, yeah.
Okay, so just a small aside and go. Oh, and I'm probably gonna be a little salty tonight. If that doesn't bother you, good. So we're gonna talk about orbits first, and let's start with the big thing about orbits. I'm gonna put it this way: when it comes to the actual exam, orbits is the crapshoot. If they ask an orbit question, they could go anywhere they want with it. It can be kind of challenging, and we all know that because one of the things that's been happening recently is because of the way they dropped out some of the material out of the AP1 exam. A lot of, well, I feel like orbits is one of those things that can be kind of thrown in there. And the C exam and the AP1 exam, they do mimic each other a little bit. So let's talk specifically about what an orbit is. And then we're going to get more and more specific and more particular. So we're going to start with a very general approach about what an orbit is and what we can expect from an orbit question. And then we're going to get to a point that's more and more particular, which means every time we change this, we're talking about a more focused subset of orbit questions. Does that make sense? So when we start talking about orbits, the first thing that I want to kind of put in your ear here is that an orbit is a combination of factors. And there are stable orbits and unstable orbits. So an orbit, generally, when we say the word orbit, we consider something that is stable, that repeats itself over and over again. So that whatever happens here is going to happen the same way every time. It starts with the idea that an object gets trapped in the gravitational well of another object. So for most of our discussion, we're going to make the assumption that small m refers to the satellite and big M refers to the object that is being orbited. So a planet and a sun, I'm sorry, a planet and a satellite, or a star and a planet, something like that. So we have something where generally this is going to be the rule, that the thing at the center has much more mass than the thing that is orbiting. Good so far? All right, so in general, they're Kepler's rules. And Kepler's rules aren't laws. They're really kind of a set of rules, although they are called laws. They are a proof worked out through mathematics, meaning they work the same way every single time. So we call it a law, but it's just a lot of observation and the result of that observation when you apply mathematics to it. And the first law, and most appropriate here, is that all orbits are elliptical with a central object at one of the focuses, whatever, octopi, octopuses. Now, that doesn't tell us very much, but it actually says quite a bit, because a circle is a form of an ellipse. It's just a special category of ellipse. So all orbits are elliptical. When we talk about an ellipse, remember that there's something called eccentricity. Eccentricity is a ratio of this distance to this distance. So it's always a value that is 1 or less. So an elliptical orbit that isn't circular has an eccentricity less than 1. So that's what we're talking about right now. One of the things that we have to remember is that no matter what, there is an unbalanced force that is causing an acceleration to the satellite. So for the rest of this discussion, the thing at the center is a planet, the thing that is orbiting is a satellite, and that's how I'm going to refer to them. You just have to, I just need a way of having a common vocabulary here. Are you guys okay with that? So big M, planet, little m, satellite. So when we talk about the net force, we are focusing on the satellite and what's happening to it. So in the condition that I've drawn the diagram so far, the object has a tangential velocity, meaning tangent to the ellipse, and is experiencing an unbalanced force towards the center. As the object travels, that unbalanced force is getting smaller as it gets further away from the planet. But also, that velocity is being acted on by a net force that both is causing its direction to change, but also causing its speed to change. So in the position that I've put it in right now, we'll call this position B, its velocity is getting smaller, and its direction is also being changed by this unbalanced net force. Eventually, it's going to make it to a position over here. Maybe over here, where its velocity is perpendicular to that unbalanced net force. At this position, we know that the net force is smallest. Because it is furthest away from the planet. So the separation distance is as small as it's going to be. Its velocity is also smallest. Again, because it's furthest away. And more of the energy is now gravitational. Now remember, gravitational potential energy is negative here, but it's the smallest negative number it's going to be because it's furthest away. So let's have a quick reminder at the bottom here. Kinetic energy is going to be based on velocity. That's still always going to be a positive number. But gravitational potential energy begins from the very start of this problem as a negative number. So the bigger R is, the smaller the negative number is, the closer to zero it is. Which means at this point, the potential energy is as large as it's going to be because it's the smallest negative number. I know that's rough to understand, but remember, we have decided if this was a roller coaster, and I know that it's hard to sometimes put all this together. If this was a roller coaster, you would always say that the object had the most potential energy here and had a lot of potential energy here. And it would have the maximum kinetic energy here. So A, B, and C. Well, that's still true, even if we put the reference level up here. If the reference level was way up there, and I called this 0, it still has the most gravitational potential energy here, because it is the smallest negative number. You guys follow that? And that's still true for every other part here. We can set the reference level wherever we want. We just need a common reference level. So if it's up here, then suddenly this is H and H is negative. And this is H and H is still negative. And this is H and H is still negative, making this the largest negative number, least amount of potential energy. And here, the smallest negative number, most amount of potential energy. We good? So that's what's happening here. We set the reference level at infinity. It's closest to infinity here. Because it's closest to infinity, it has the most amount of potential energy. Over here, it's furthest away from infinity, least amount of potential energy. So here, velocity is greatest. Potential energy, least. Force, greatest. We okay? Now that is, in a nutshell, the balance that's taking place that occurs during an elliptical orbit. Now, one of the things that I need to kind of impress upon you is there are relationships that occur during this orbit. But consider the direction of the net force acting on the system all the time. The net force is always acting towards the planet. This net force can change the velocity of the system. But because of the direction it acts, it can't change the angular momentum of the system, because the force is always aligned with the torque arm. So it can never apply a torque. And because it can never apply a torque, the angular momentum, either capital L or lowercase l, is a constant. And it doesn't matter whether I use capital L or lowercase l. The angular momentum of the satellite doesn't change no matter where it is. Now, this is where we have to, where stuff just gets a little complicated. The angular momentum can be written either as capital I times omega, that's fine, or it can be written as R perpendicular mv, that's fine too. And the reason is straightforward. I omega is going to be m r squared times omega, or r mv. R perpendicular in this case is just whatever r is, the distance away from the planet. Now, if you look closely at this, you realize that omega is v over r, so they are the same. So it doesn't matter whether you consider this in terms of the angular speed or the linear speed. They're both changing because r is always changing. Now that's an important detail, because that means that over here, I have r far, m v far. And over here, I have r near, m v near. The angular momentum has to be the same. And because the angular momentum has to be the same, when r gets small, v has to get big. And when r gets big, v has to get small. And it's a direct proportion. So if r is 3 times bigger on this side, then v is 3 times bigger on the other side. It is a direct proportion. And all of that depends on whatever the ellipse is. So it's really not that complicated, but it is, because we know there's a complicating factor here. And that complicating factor is the fact that energy is also conserved. Now, I'm going to pause for a minute. Has all of that sunk in? Are we good so far? Am I going too fast or too slow? This is the pace I'm going to keep. All right, so let me throw something down here for you so you understand. You can always set these two things equal to each other. In any orbit, that's got to be true. So if you have both R's and one of the V's, you've got the other V. When it comes to orbit questions on the actual AP exam, they've been really light. They've really never dived into a deep orbit question. I think they figured that there's enough that's difficult to deal with the potential energy being negative, that they really don't want to work too hard at asking you a tough question. But there are tough orbit questions out there. And if you want, I have one cooked up sitting on the side we could look at. But what I really want you to think about for the most part is, in a problem like this, it's really a bunch of ratios. And you see that, right? It's the ratio of R near to R far and V near to V far. What's really important is that they're never going to ask about positions like this one or this one. And that's because the velocity and the force are not perpendicular to each other, making those positions difficult to deal with. But be mindful, R, M, V still has to be the same right here. That's the one thing that has to be true everywhere on the ellipse. RMV has to be true. So over here, the velocity is becoming a smaller number. It is, I hate to use this word, decelerating as it goes around the circle. But ultimately, RMV has to equal whatever it is over here and whatever it is over here. And that's true everywhere in the circle. Now, let's make all of this smaller. Maybe. Oh, that didn't really work out, did it? Why did it grab some of the stuff and not all of it? There. Because while all of that's going on, we've got potential energy plus kinetic energy equaling a constant. And that's true everywhere in the circle too. And although momentum is a vector, when it comes to an orbit, that's less useful because the direction is always tangent to the curve. Energy is not a vector. So we've got minus big M, little m, G over R squared plus 1/2 mv squared. That's true everywhere. So that's true over here too. Minus mmg over R squared plus 1/2 mv squared. What you have to understand is, although these two things are the same, meaning they equal the same amount, they're going to be both negative. If you're in an orbit, you are trapped in a gravity well. And if you're trapped, your energy is negative. The only way your energy could be positive here is if you've made it to the infinite location, the reference point. So we assume that since our measurements are made relative to a point at infinity, that the only way your energy could ever be positive is if you've ever completely escaped the gravity well. And you are now outside any possible indication of being attracted to the gravity well. So these numbers are always going to be negative, always. Now, that being said, that is the elliptical orbit stuff. There's a little more I can talk about, but are there any questions up until this point?
I have a question about the kinetic energy, because I know
Go ahead.
In the physics book, they also used G big M little m over 2R for kinetic energy.
That's be careful. That's only for circular orbits.
Okay. Okay.
So, and we're going to get to circular orbits in a minute, but in this scenario, that's not true, and you can't count on that.
Mm-hmm.
Okay.
Mm-hmm.
All right. So there's something else I need to play at, but it's going to take me a few minutes to draw it. So give me a few minutes. And by minutes, I mean like 30 seconds. I finished my coffee, by the way, so you know that's bad news for all of you. Okay. Are you really ready to get into this now, right? Because this, what I'm looking at right now, is the problem they could ask. They've never asked this on an AP exam, but they could. And considering that I think it's a traditional exam, I don't think you're going to see this, but I want to talk about it. Let's talk about circular orbits for just a minute. Now, this is a subset of orbits. And we know that there's a difference here. In these orbits, the net force equals MAC. There's several implications here. And by implications, these are like subsets. If these things are true, then it's a circular orbit. Thing number one, the net force is not just related to gravity, but is equal to mv squared over r. That means R is constant. V is got a constant magnitude. K is constant. U is constant. And we know their sum is a constant, but the individual values are constant. And as always, the angular momentum is constant. But the special things here is that each one of these by itself is constant. The velocity never changes. It's the same speed all the time. R never changes. It's the same distance away all the time. That's what makes a circular orbit special, because those things are always going to be the same. Now, that being said, let's talk about some implications. We'll pick one of these, and I'm going to say that we're going to start with this R right here. We're going to call this R1, or no, let's do R close. And this one, R far, okay? So two possible orbits, a close orbit and a far away orbit. We know ultimately that when you are in a circular orbit, this has to be true. This has two important implications. So I'm looking at just the close orbit. So right now, our object is right here with that velocity. Okay? It's experiencing whatever. It's experiencing a force. It's in a circular orbit, blah, 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 blah. We know that the velocity close has to be equal to a value of mg over r close under the square root. That's what you get when you take this and solve for v. Good? No worries? At the same time, since v equals 2 pi r over t, we can, by substitution, show that period equals 2 pi times the square root of rc cubed over mg. Do I need to do the math on that, or are we good on that? I'm good either way. This is when you solve this for t and substitute that in for v. You good there, Xavier? Okay. So those two things have to be true. Think of the implications. First, the period is related to the radius cubed. Further away, period gets bigger. Not a surprise. The further you away from your orbit, it's going to take longer to go around. And there's two reasons for that. First, look at this one. The further away you are, the slower you have to travel to maintain a circular orbit. So the farther away, the force is smaller. The circle you're traveling is bigger, so your velocity is less. And because your velocity is less and the circle is bigger, the time it takes to go around takes longer. We're good so far? All right, so keep this in mind. That also means for a circular orbit, the energy doesn't keep changing between gravitational and potential. The energy is a fixed amount of potential and kinetic that stays the same the whole time. So the total energy is mg over rc, and that's negative. And the kinetic energy is 1/2 mvc squared. But as it was pointed out a minute ago, Vc is a particular value that is related to the mass and R. So you could square that and substitute it in right here. And when you do, lo and behold, you get E going on here? You get E equals negative mmg over RC squared plus square this number, put it in with the 1/2 m, and you get mmg over 2 RC. Sorry, I put a squared there. There's no squared there. So this is what happens when I take this and put this in for V. And yes, you get this kind of interesting value for the energy. But don't read too much into this. This is only the energy for a circular orbit. It is not the energy for anything else. We okay? All right. Here's where it gets interesting, I think. If I want to transition from this close orbit to the far orbit, then I want to do something where I increase my velocity. I want to be faster than the force would require us to stay in a circle. I said that kind of weird. I kind of fell apart on it. Let me say it again. I want to travel faster so that my path is too fast to curve in a circle. I want to fall outside the circle. And I want to do so in such a way that it takes me to a new position here that might be at a new distance away where I'd like to be in a different orbit. This is a translational orbit where I'm going from one circular orbit to another circular orbit. Now, to do that, I have to increase my velocity to be greater than VC. This makes me fall outside the circle. I'm going to get up here though, and when I do so, the rules of orbits, R, C, M, VC, has to equal what I hope will be my new R over here. Remember, I'm increasing my velocity so that I'm going a little bit too fast, but I'm still at RC right there. That's going to push me out to this location here. It's going to make R get smaller. I need R far. This is going to be, I'm just going to put V2 for a minute. So this is V1, and that's going to be V2. When I get out here, I'm further away from the planet. But because of this ratio, my velocity has also decreased significantly. So I am no longer able to sustain a circular orbit. I'm going to fall underneath the required velocity to be in a circular orbit. That's what creates this elliptical orbit. The fact that I'm now not fast enough on the outside to be in a circle, but I'm too fast on the inside to be in the circle. Oh, I would love it for somebody to bring me some ice cold water. That would be fantastic. Could you just have him, slide on over here with that? I mean, I've got my empty cup here. Just flaunt it in front of me. Nice, nice. All right.
I'll pour you some to the screen.
Oh, that would be wonderful. So if you wanted to go from a elliptical orbit to an outer orbit like this, when you reach this point, you would have to know how fast you need to be traveling in order to now increase your velocity to match the outer orbit. But it's not a surprise. This is still true over here. So the orbit the velocity you have to be at that orbit. So this is how you transition from an inner orbit to an outer orbit. You make yourself go a little bit faster here, fast enough where the outside orbit is what you want to attain. You wait till you get there, then you fire your engines again so that you get to the velocity you have to be in this orbit. Now, that's a lot, but believe it or not, that's it. That's all the orbit stuff that can possibly be on the test, every bit of it. And let me sum up. There are 3 different things you have to know about orbits. Thing number 1, you have to know that circular orbits are special and have a specific fixed velocity and a specific fixed period. That's the first thing you need to know. The second thing you need to know, most orbits are elliptical. And because a circle is an ellipse, the following two things are true. Angular momentum is conserved, so RMV equals a constant. That's a fancy way of saying is RMV at one place equals RMV at another place. Energy is conserved. Again, a fancy way of saying that potential plus kinetic is equal to a constant, or negative mmg over r plus 1/2 mv squared equals a constant. For a circular orbit, that produces something special, that the energy equals negative mmg over 2r. Boiled down, that's what you have to know for orbits. Keep one little thing in mind. You guys are pretty smart people. And I like the fact that the smart people showed up tonight. Can I just show you something that's just kind of silly? I'm going to grab this for a minute. Remember that this is r cubed over mg. Do these things remind you of anything? Those all look familiar? You do see how they all look exactly the same. Inertia, restoring force. Right, they're all like that. If you put an M and an M here, you totally see that that's the force of gravity, and the top is close to the moment of inertia of a point mass, right? ML squared would be the moment of inertia of a point mass. We just have ML. Well, if you look at gravity, just take two of those R's away and put them down there. And then put an M here and an M here for the satellite. Do you see what I'm trying to point out? Inertia, restoring force. It's still just like a simple harmonic oscillator. Every simple harmonic oscillator obeys the same principle. A relationship between inertia and restoring force. And the only reason that these aren't squared is because of geometry. It comes down to the small angle theorem. Takes away one of the R's or one of the L's. So I just want to make sure you see that there's an incredible symmetry here. Okay? All right. I think we've been pretty thorough about talking about the orbit thing now. Can we do something else? Or is there a particular question that you want to ask me about orbits? Because I'm reading boredom out there, and well, it is a Saturday night, so. Going on, period ideas in general. Did I just do that?
Can you go over like the omega thing?
The omega thing, yes.
Okay.
The omega thing. The W with a flare. Got it. So let's talk about the omega thing. The omega thing is it's a generalization. It comes from seeing that there is a solution to this relationship, right? When we did this for a spring, this was K over M. We found that in solving this, the solution for X produced this, right? We guessed at it and found an answer. It ended up being that we take the second derivative and it produces a negative sign and some constant. Because it took two derivatives to do that, whatever's here has to be squared when we put it here. But it's more important than that. We said, okay, there's some constant that has to be here. Let me stop thinking about it as a spring and a mass and start thinking about it as some constant, some value. The reason that value was important is because whenever the inside of this is 2 pi or some multiple of 2 pi, my system has come back to where it started, right? So the first time that happens, from t equals 0 to t equals capital T, which I call the period, the first time that happens when omega times t equals 2 pi. That is the first repeat of the system because it's a cosine. Whenever the inside of that increases by 2 pi, we have returned to our starting point. So we said that whatever this constant happens to be, the period is 2 pi divided by that constant. Now, we based all that on a spring, but the truth is, it's any constant here. Whatever the second derivative produces as a constant, that is whatever we need to figure out the period. That's why when we talked about a pendulum, we had that net torque on the pendulum equals I alpha. What was the torque? And I don't want to draw a picture, but I will because you're paying me the big bucks to be here tonight. So I'm making lots of money talking about physics on a Saturday. I'm making no money. I care about money. Actually, I'm making 50 bucks a piece. That's right. Keep it. Come on. Eye on the prize, Mr. Shelton. Eye on the prize. 50 bucks a piece. 50 bucks times 21 people. Yeah. That's something to talk about there. That's a new tattoo all the way. So when I look at this, the net torque is going to be, let's see, negative, and I get a LMG sine theta equals I alpha. Good so far? Well, I don't want to use sine, so I use that small angle approximation. My pal, small angle approximation, and I get minus LMG theta equals I alpha. Doing good so far, right? Good. So I'm looking at this and I'm thinking, okay, I want to make it look just like that. So alpha equals negative LMG over I theta. Pretty close. Let's make it look even closer. Get rid of that alpha. D squared theta over dt squared. There it is. I've done it. I made this out of this. This has got to be omega squared. It has to be. So, wow, this is a mess. Let's make it look smaller because that makes it better somehow. So omega squared equals LMG over I. So I just do what I have to do here. T must be 2 pi divided by omega, which means times the inverse of this under the square root, I over mgl. You still following? Because I did a lot there. But I is just ml squared, right? It's a simple pendulum. It's a point mass. So 2 pi times the square root of ml squared over mgl. Now, I thought by coming at it a different direction, you'd kind of see the connection to omega. You know, we knew we were going to get L over G. It's a stupid pendulum. The important distinction is I need to see if there is some constant that exists. That when I take the second derivative, I get this constant. The square root of that constant is omega. And any place omega shows up, I can put the square root of that constant there. So it shows up in a lot of places too. You know that, right? When we look at our thing, we have not just period, but period is one of them. And period tends to be the one that they focus on. And don't forget frequency. But there's also Vmax, right? That's A times omega, where A is the amplitude. There's Amax, the max acceleration, and that's A times omega squared. All the result of looking at those motion equations. But there's something else here too. Omega is a frequency. It's radians per second. If you look at this formula, this is actually your conversion equation to go from oscillations per second to radians per second. It's your conversion fact. You've always known this, that if you want to go from radians to degrees, radians to degrees, you multiplied by 2 pi and then divided by 180 or something like that. It's the same conversion fact. We're just using the 2 pi in the same way. So if I have oscillations per second and I want radians, well, there's 2 pi radians in one oscillation. So I multiply by 2 pi. If I have, radians per second and I want to get oscillations per second, I divide by 2 pi. That fact you've already known. It's just kind of funny that it happens to be also the foundation for simple harmonic motion. And it's why the 2 pi shows up. It's circular motion all the way, all the time. So Victoria, did that do what you needed it to do? Thumbs up, I like that. All right, back to our list of stuff we want to talk about because we're having fun. Negative, positive work.
Just like how you can tell the difference between negative and positive work. Yeah.
I had a feeling. So
yeah.
It shows up in weird places, and it tends to show up when you least expect it. So let me start off by saying the AP Physics C exam has already been written. It was probably written 3 months ago, maybe longer. And it wasn't written by one person. A whole group wrote that exam. They sat down, they thought of all the things they wanted to have on that exam. They started coming up with questions. They probably wrote 15, 16 FRQs, and they looked at hundreds of multiple choice. And they narrowed it down to the test you guys are about to take. Nothing in that test was just like, well, we need something else here, let's throw something in. Enough people looked at it where every single question was in order to see if you knew something. Does that make sense? So don't take this for granted, and don't in any way think that the question that's put in there was too easy or too hard. It wasn't either. It was, do you understand? Do you know this physics principle? What we saw on Friday was it's easy to let your gut tell you an answer. And when you do that, you run the risk of not recognizing that every single answer to the AP exam needs to be based on a physics principle, not your gut. I'm not saying not to trust what you think should work. I'm telling you on something like this, be careful of trusting your gut. Because this is where it gets, where your gut can lead you the wrong direction. Work has a definition. We have defined it. And because it's something that humans have defined, the negative and positive isn't intuitive. We have set a standard and we expect you to follow the standard. So the first definition, work equals an integral. This is negative when the force and displacement are not in the same direction. Period. This only works out to be negative when the dot product is negative. So that means cosine of theta. If the direction of the force and the displacement is less than 90 degrees, the work is positive. By definition, by no other reason, but definition. If the angle between the force and the displacement is greater than 90 degrees, the work is negative. By definition. No intuition, definition. You can count on it. So when we did that orbit a minute ago and the planet was here and the velocity was this way, work was being done on the planet. The energy stayed constant, yes, but the work being done was to change kinetic energy into potential energy. And the force was this way, greater than 90 degrees. The work done on the planet was negative to convert kinetic energy to potential energy, period. That's why work equals the change in potential energy. That work done became a positive change in the potential energy, making it less negative. Right? All of this has to work to be consistent and the same every single time. Go ahead, Victoria.
So if we were talking about a circular orbit and it asked us about work, the work is always 0, right?
Thank you. Yeah. Notice I didn't say anything about 90 degrees. I purposely stayed away from it because the cosine of 90 is 0. No work is ever done if the force is perpendicular to the displacement. So there is never an exchange of kinetic energy and potential energy in a circular orbit because the force is perpendicular to the velocity. Does that make sense?
So work
then
is only
which-
done when the velocity changes magnitude?
Okay, I flip that around. You said work is only done when the velocity changes magnitude. I would rather you say it that if the velocity changes magnitude, you know that work was done. I want to be really careful about this because absolutes are hard in physics, right? You understand that. Throwing that word only in there suggests an absolute, and I don't want to suggest an absolute where there might not be one. But what I do want to do is talk about the second condition where work is done. And it's not a condition. This is the definition of work, period. So if you know
Mr.
work is
Shelton,
done, yes.
I had a question about the picture that you had up before.
Oh, well, sorry. Allow me to backpedal.
Which angle would we use?
Okay, it's the angle between the velocity and the force. So this one.
Okay.
Okay. That was it? I went back just for that? Okay. Now, the next thing I want to say is that we have a theorem. And the theorem isn't a definition. It's the result of applying a definition. That's what, theorems are like that. And it's the work energy formula. And it says if net work is done, then that results in a change in kinetic energy. Net work. I need to be careful about the way I say this because remember, this is about a single force doing work. This is about an unbalanced force doing work. So this refers to a second law condition. But the implication speaks to what Xavier just asked. Any change in kinetic energy means work was done. So if the kinetic energy increased, positive work was done because K final is greater than K initial. So positive work was done. Any attempt to slow the object down, negative work was done. K final was less than K initial. So you can count on positive and negative work just by looking at the change in kinetic energy. That has to be true. And there is no exception to Xavier's comment. That's an absolute. If the change in kinetic energy is positive, positive work was done. If the change in kinetic energy was negative, negative work was done. Now, put that together with this. If an object's kinetic energy increased, meaning positive work was done, the potential energy had to decrease. That's what that says. That's what it says right here. If the work was positive, the change in potential energy was negative. Don't think too hard on it. You drop a ball. If you drop a ball, it starts with a kinetic energy of 0, and it makes it down here, it has lots of kinetic energy, right? Its kinetic energy increased. What happened to its potential energy? It definitely decreased, right? It's closer to the ground. So a positive change in kinetic energy has to result in a negative change in potential energy for a system that is, like this. Same would be true for a spring. If you have I don't know. I need something here. I need a picture. I need something here and a spring and something like that in the box. Box has got kinetic energy. No, the box hits the spring. So that means that as the result of hitting the spring, the box stops. Right? So the kinetic energy is now 0. Change in kinetic energy is negative, which means the work is negative. That means the change in potential energy is positive. Has to be. That energy is now inside the spring. What I didn't emphasize enough this year is that the work energy theorem is conservation of energy. When you combine the work energy theorem, this, with this, you find that any change in kinetic energy has to yield a similar change in potential energy. Always. If you look at this for a minute, and this should not freak you out, but it might, because I'm hopeful. This is K final minus K initial equals minus U final minus U initial. We good? You see that okay? I know Xavier, you're straining, sun's in your eyes. What are you drinking there, Joey?
Also some water.
Oh, I'm gonna need to go get some in a minute. You guys see what I just drew there though, right? You're following it okay? And you know that that negative sign is just gonna do this, right? Good? So I'm gonna put everything positive. So I'm gonna move this over here and this over there. And I get K final plus U final equals K initial plus U initial. Right? The state of the energy before equals the state of the energy after. All of those things have to work together every single time. And I never threw that in your face, but it's got to be true. So the whole positive negative work thing has to play to this. It has to live here all the time. Even in E&M, this has to be true. So how is that for negative positive work? All right. Look, folks, I am going to get myself some water. So Victoria has her hand up, of course.
Why isn't it network equals the change in potential?
Okay, that's a good question and worth me discussing. So let's deal with a more complicated work question. And then I'm going to take a break for some water, okay? So first, let's handle the idea that work can be done by an individual force, which means that you could have this arrangement. Not that arrangement, this arrangement. Let's make some really, really terrible force problem. Okay, so quickly, and 12, and so 20 newtons, 25 newtons. There we go. All right, you guys see my question here, or my setup? Do me a favor. This force pulls the box 10 meters across the floor. Now I'm using straightforward numbers, but I'm using numbers here to prove a point, okay? So I wanna do two things. I want to consider energy for just a minute. So let's do energy for just a minute. I want work done by F. Pretty straightforward. The work done by F is going to be 25 newtons because it's a constant force. I don't have to integrate. Times 10 times the cosine of the angle, 30 degrees. That is the work done by the 25 Newton force. Any questions about that? All right, so one of you guys has got one laying around. Throw that into a calculator and spit me out a number in joules. You can't just look up and make that happen, Xavier. It's not going to happen. I mean,
It's 5 times 25, isn't it?
No, it's square root of 3 over 2. Cosine of 30.
It's 38.
Yeah.
That's what I was looking.
I know. Yeah, I know. So come on. Fire it up for me.
216.5.
216.5 joules. Great. Now, friction is acting in the same system, right? Normal force is 50, but we have to deal with the fact that we're pulling up on it. So the actual normal force, because of net force, is going to be 50 minus 25 sine 30. Right, that's normal force. Just did net force on it. Sine 30 times 25 is 12 and a half. So 50 minus 12 and a half, 37.5. So friction also is doing work. That's going to be 37.5 times 0.25. That's the frictional force, times 10 times the cosine of 180 degrees. Mu n times d times cosine theta. How much work was done there?
Negative 93.75.
Now, here's the takeaway. I put numbers in here to distract us. Our pulling force did positive work. Why? Because the angle of the work was less than 90 degrees. And therefore that force did positive work on the box. At the same time, friction applied a force to the box, and that force was negative. I'm sorry, that force was greater than 90 degrees. It was 180 degrees. So the frictional force did negative work on the box. But the result is a positive number because more positive work was done than negative work. Now, what that means is, if we look at all the things that happened, net work was done on the box. This box is moving with a velocity at the end of this. Because we know that the work that was done by friction, which took that energy away, was not enough to overcome the amount of energy I gave to the box. The box finishes with residual energy. That residual energy has to equal 1/2 mv squared, which is the final kinetic energy of the box. Now, don't take this too far, but that's not a surprise. Second law says that net force equals ma. Our force acting forwards on the box was 25 cosine 30. The frictional force was mu mg, 0.25 times 37.5. This has to equal ma. Our box is accelerating the whole time. You plug that into your calculator, you get a positive acceleration. In fact, I bet you plug that into your calculator, you can get that positive acceleration. You're going to find that that acceleration plus a delta x of 10 meters plus an initial velocity of 0 and a final velocity will give us the same final velocity this will. And it has to. Why? Look at the equation you're going to use. 2a delta x equals v final squared minus v initial squared. Look familiar, right? It's one of the motion equations. Divide by 2, multiply by m. ma delta x equals 1/2 m v final squared minus 1/2 m v initial squared. Net work done, Newton's second law right there. You good, Victoria?
But then how would work done by, let's say, just the force be negative change in potential?
In this case, the box's potential energy never changed. Right? It never changed height. Now, if you need to see what you're asking, I can come up with a simple example of this. Same box. 5 kilograms. Can't use the same force though. Let's use a upwards force of 50. No, let's make it 60 newtons. And I'm going to lift the box 10 meters. I can't use 25 newtons. A 25 Newton force wouldn't lift a 5 kilogram box, right? 25 Newton force can't pick up a 5 kilogram box because a 5 kilogram box weighs 50 newtons. So I'm using a force greater than the weight of the box. Now, the work done in this case is pretty straightforward. The work that I do is 60 newtons times my distance of 10 meters times cosine of 0 degrees. That's how much work I've done. Good so far? Now, do me a favor, that's 600. At the same time, that is not the work of the net force. That is the work of my 60 Newton force. The net force on the box is 60 newtons minus 50 newtons. Because there's two forces act on a box, a 60 Newton force and a 50 Newton force. 50 newtons is the weight of the box. Am I okay so far? So the net work is 10 newtons times 10 meters times cosine of 0 degrees, which is 100 joules. Good? Well, how much potential energy does the box have when it is 10 meters above the ground? M, G, H. How much work was done on the box by gravity? Gravity did negative 500 joules of work on the box. Taking the 600 joules of work I did, took out 500 joules and left me with 100 joules. Where's that energy now? Kinetic energy. The box is still going upwards. It's got a velocity. And of course, I would know that because the other way to look at this is I hit the box with 600 joules of energy, and that has to be split between gravitational potential and kinetic, which would be mgh plus 1/2 mv squared. Conservation of energy will still work. We good? All right. Guys, I'm gonna go get a cup of water. I will be back in just a sec. Let's go back. What did we see? We have overview of torque. Overview. So, you know that entire conversation we just had applies to torque, right? That torque can do work. We didn't talk about this enough, but I don't really think, they don't make questions like this, and they should, because net torque equals I alpha, which means that work could be written as the integral of torque dot d theta. Now the dot product here is a little ridiculous because, I mean, the torque is either in the direction it's going to rotate or not in the direction it's going to rotate. It's not like it's, that part's a little weird, but it's still applicable here, that you can change the object's rotational kinetic energy by applying an unbalanced torque. So everything we just talked about is applicable here, except we don't really have a good form of rotational potential energy. The only kind of form we'd have is if we had some kind of torsion spring. And although I've thrown that in front of you, that's pretty esoteric. That's pretty unlikely to show up somewhere. On the other hand, one of the big things I think that gets missed here is that there's visible torques and there's invisible torques. Unlike force, you can have an invisible torque. Let me show you what I mean. A visible torque is obvious, right? I try to balance a meter stick on a point that is there. It won't balance because the center of mass of the meter stick is over here. It applies a torque. How? Well, gravity acts at the center of mass. Now, let me get all the eyeballs for a minute. Gravity does not act at the center of mass. That's BS. It's a lie. It's a mathematical construct because it works. And it's simpler than saying that gravity acts on every piece of mass all over the stupid meter stick. It just so happens that there's more meter stick on one side than the other. I mean, truth be told, we could break the meter stick in half and say that it acts on the center of mass here and the center of this mass here, and it would still work. It would still be the same because gravity acts on each piece. We have simplified it. We've simplified the math. And the math tells us that if we calculate the center of mass of the system, we say that that's also the center of gravity of the system, and we can use the center of gravity like it's a torque and a point mass by finding the torque arm length to the center of mass, using gravity as the applied force, recognizing that the angle here is the angle between the torque arm and that force. So torque is a combination, taking into account the direction of the applied force. But there are invisible torques, torques that you can't see. Now, I don't want to come up with any kind of crude example because I really could. But if there's something twisting and you wrap your hands around it, that's a torque. It's friction between the surface of your hands and the thing that's rotating. It's harder to imagine that though, because you're applying that torque all around the object. I really can't isolate a single force there because the friction is acting along that entire surface area. I know that most of you have put on roller skates before and you've spun the wheel before. The wheel didn't spin forever. What was slowing it down? Well, inside it, there were ball bearings and they were all bouncing around and they were applying this hidden torque. The problem with torque is that there's sometimes torques that you just can't easily see that occur at the axis of rotation. And so they can throw that into a problem and say that there is a torque acting on the pivot point, on the pulley, one that you can't see, a frictional torque generally, that's causing the object to change its rotational state. But don't build that up to be anything more than it is. Torque is Newton's second law and Newton's first law. If there's an unbalanced torque, the object will accelerate. It'll spin faster or spin slower. There's a balanced torque, the object will spin forever or not spin at all. It's that straightforward. When we deal with torque, you can replace any sentence that deals with torque with the word force and you'll get the same response. So there's the practical. Kid stands here, applies a force to the edge of a merry-go-round. The torque applied there is going to be based on this torque arm length, the radius of my merry-go-round, and the moment of inertia of the merry-go-round will determine what the resulting acceleration is going to be. So I get R times F equals I alpha. Good so far? Torques can be incremental, but they can also be sudden. The kid runs towards the edge of the merry-go-round, jumps on the merry-go-round, and now the merry-go-round is spinning. There was a torque applied to the merry-go-round. How do I know? The merry-go-round is spinning now and it wasn't spinning before. Anytime there is a change in the angular speed, there had to be a torque, period. I don't have to know what applied the torque to know that there had to be a torque. This is also true for an object. If an object's velocity changed, there was a force. I don't care if the force was conserved. I don't care if energy was conserved. If the velocity changed, there was a force that acted. That's true here too. So the kid jumps on the merry-go-round. Now the merry-go-round is spinning. I know there had to be a torque. What was the torque? Well, probably friction between his feet and the merry-go-round for an instant until he came to rest relative to the merry-go-round. He was pushing on the merry-go-round with the frictional force. At the same time, merry-go-round was probably pushing on him with the frictional force. Probably slowed his linear velocity down because the merry-go-round had inertia and it was hard to get it moving, which meant there was a net torque here. What's interesting is that once he joined the merry-go-round and the merry-go-round decided that it had an angular speed, he could walk towards the center. We know him walking towards the center is going to speed up the merry-go-round, right? The moment of inertia is going to get smaller, angular momentum is constant. So I omega initial has to equal I omega final. He walks towards the center, moment of inertia gets smaller. By definition, angular speed increases. Any change in angular speed means there was a net torque. There was a net torque there. There had to be. The angular speed of the merry-go-round increased. So the merry-go-round experienced a torque. The kid also experienced a torque because when he's here, his velocity is smaller than his velocity is on the edge. He experienced a torque too. it slowed down not his angular speed, it slowed down his linear speed. But because his moment of inertia is smaller, his angular momentum is smaller too. So just him, his I omega is less than it was before. I want you to think about this for a minute, because it's kind of a weird thing. And I never really talked about it because it didn't really occur to me until I really was thinking about this the other day. When he first jumps on, we have the initial angular speed. He walks to the center and we have the final angular speed. We could work the numbers on it. But let's see if we can just do this as a thought experiment for just a minute. It's I for the merry-go-round plus I for the kid times omega initial equals I for the merry-go-round plus I for the kid equals omega final. We make the kid's moment of inertia smaller because he's a point mass. His moment of inertia is mr squared. He walks towards the center, r gets smaller, his contribution gets smaller. So everything in the parenthesis gets smaller when we go from here to here. That means the angular speed had to get bigger, had to. But look at the kid. The kid's angular momentum is I kid times omega, or mr kid squared times omega. So angular speed went up, but r got smaller and then was squared, which means that his angular momentum is less. Has to be. But the angular momentum of the merry-go-round increased. Why? Because its moment of inertia didn't change, but its speed got greater. But the change in angular momentum of the system, 0. Has to be 0. There had to be a torque. There was a torque on the merry-go-round by the kid and a torque on the kid by the merry-go-round. Why? Their individual angular speeds changed. Now, somebody asked me to talk about an overview of torque. To me, that's an overview of torque. It hit all the high points, but that might not be what you were hoping for. So whoever you are, what would you prefer I really kind of dive into here? Because that's a pretty open statement. Diet Dr. Pepper cream soda. My wife swears by it. I on the fence, but I wanted something bubbly, and it is it checks off the box of bubbly. Wanted some with caffeine. I think there's some in there, but it is neither Dr. Pepper nor cream soda. It's some horrible hybrid Frankenstein model of the middle. It's not pleasant. It's not great. But I wanted a soda, and now I have one, and I am not happy with the results. So there. That's now in the video. So when I post it later on YouTube, I guess whoever makes Diet Dr. Pepper and cream soda can come after me for royalties. So nobody said anything about the whole torque thing. So I'm thinking either, oh, finally.
I just have a question in general. If we were given like a system, like let's say it was like a sphere that was like rolling down a hill, and it does, like the question doesn't explicitly say like there's friction acting on it, but they want us to draw like a free body diagram, do we always just automatically say that there's like a friction going in the opposite direction of motion since it's rolling?
Not just no, but heck no.
Okay.
Pay particular attention to these questions. They are not going to make this subtle, but they are going to try and be tricky. We've seen that before. So rolling questions are particularly troublesome because it seems to be a place where test writers want to really see if you have a good understanding of the interplay between translational motion and rotational motion. And here's where it's no gray area, but it is definitely an area where it's at the edges of what we talk about a lot, because it can get down to the nitty-gritty here. If they don't mention friction, you need to look for context clues to figure out whether our system actually is a rolling system or not. Does that make sense? So if they don't say something, be careful. Be very careful. If there's no friction here, then this is no different than a box sliding down the ramp. And therefore, its kinetic energy down here at the bottom is only going to be translational. So we would say that its velocity down here, this direction, this velocity, is mgh equals 1/2 mv squared. Now, that would mean then that the forces acting on our system would be only those two.
Okay.
And the net force would equal MA, and I would get mg sine theta equals MA, and A is going to equal G sine theta. Now we start there because I think it's important to understand that it's traveling faster than it would travel if it rolled. Because if they tell us that it's rolling, they are sending you a statement that friction is acting.
Okay.
So they don't have to say that there's friction, but if they tell you it rolls, they are telling you there's friction. And when they tell you that there's friction, they're being deceptive, because friction will not equal mu times normal force here. There will certainly be friction, but it will be less, because this is going to be static friction, which means friction is going to be less than or equal to mu times normal force. And it's going to be on the low end of that, period, unless they push us to the extreme.
Why would it
What's
be
that?
static versus kinetic?
Because it's not sliding down the ramp. This point of contact is not moving relative to the ramp. It's static. In fact, it's rolling about this point. This is our pivot point. And that point is in contact with the ramp and is not sliding across the ramp. It's rolling across the ramp. Follow the difference?
Yeah.
Because this is one of those like gray areas that I think is incredibly important. We come back now and say, okay, mg sine theta minus friction equals ma. So that alone tells us that there's less acceleration, so it's going to be traveling slower at the bottom. Now, we could do the math on that, but it really depends on what they give us that determines what I mean by the math on that. mgh is going to equal 1/2 mv squared plus 1/2 I omega squared. But it's incumbent upon us to realize that net torque is going to equal I alpha in this circumstance. Now, this is one of those things where you could decide how you want to deal with this. Do you want to deal with the pivot point being at the point of contact or the pivot point being at the center? There is no difference in the mathematics, but it's just a difference of how you feel it's happening. Do you feel the frictional force is causing it to spin, or do you feel that the weight is causing it to spin?
The frictional force.
Okay, so I'm going to take your advice and say that the frictional force is causing it to spin. Okay, the rest of you take note that that's a personal choice. There is no difference in the answer. It's just I would say it's what you feel better about. And I agree with you. It feels to me like it's the frictional force that's getting it to turn around. But some of you might feel like it's the frictional force that's holding this place in place, and it's the weight that's causing it to turn about, or actually based on the direction I'm looking at, turn about. Does that make sense? So, but I'm going with what Sana said. Okay, you guys good with that? So the torque now is based on the frictional force acting at the edge of the wheel. So F times R equals Give me a shape, Sana. I need a shape. Or I just leave it as I. It's your call.
You could just leave it as I.
Perfect. I times alpha. But I need to come to grips with alpha and A are related. So I will go ahead and put it all in terms of A. Now, here's where we make a decision. And the best decision is to group the R with the moment of inertia. So friction equals I over R squared times A. A reason to do this is because, look, we know every single version of something that rolls has a moment of inertia with an R squared in it. We leave the R there, it doesn't affect other parts of the problem. But you multiple choice haters understand that they'll screw you on this one by putting R everywhere else, by multiplying the entire thing top and bottom by R squared. Just look for that and not be worried about it. But it's easier if we do this. So now we get mg sine theta minus I over, what the hell just happened? I'm sorry, what the heck just happened? Sorry, YouTube. I over R squared A equals MA. So we get mg sine theta equals I over R squared plus M all times A. Now, this is how you get the acceleration of the system. And more importantly, this is how you find out how much frictional force there really is. It's the only way to do it. There is no way around it but this way. So if you want to find out how much friction there actually is, this is all you've got. So you eliminate A between these two, and you got the frictional force. And you find out that objects with a greater moment of inertia require more friction because they're harder to turn. And objects with a lower moment of inertia take less friction because they're easier to turn. But also keep in mind, that's also true here. If the moment of inertia is greater, then more of the energy is going to be rotational. And if more of the energy is rotational, less of it is translational, it's going slower. All the things we would expect. So whether you deal with this from an energy perspective or a torque perspective, the frictional force is still taking away the speed of the object. The difference is a rolling object doesn't lose energy to a non-conservative force. So because it's rolling, that energy is still with the object and not left as heat along the top of the surface. The only force of friction that can take away energy is kinetic friction. Static friction can't. And whoever asked about work earlier, that's why. Static frictional force can't do work. It can convert energy, but look at the direction of the force versus R. It's a weird little thing there. It can cause a change in kinetic energy, I'm sorry, a change in potential energy into rotational energy, but it can't take energy away and convert it into something else like heat. I don't want to make an absolute. I don't know if there's every situation static friction can't do work. But in this case, the work it does converts potential energy into rotational kinetic energy. I want to make sure that's what I've said.
Mr. Shelton.
It's a big yawn there, Jack, a big yawn. That's right, we're going on, hour and 45 minutes of physics. I'd be yawning too. Go ahead, Josh.
So I just wanted to clarify about as I spoke, I saw myself in the camera and I was like, but I just want to clarify about how it's static friction and not kinetic, because even though it is moving, like the point of contact doesn't move until you get to the next point of contact, like because it
kinetic
like,
friction, just come down to this. Kinetic friction, the surface slides across the other surface.
okay.
Static friction, There's no sliding involved.
All right. So
When that
'cause in
point
this
comes
case-
down and touches, it does not slide across. It stays in contact until the next point is in contact.
Okay, that makes sense. But there's just like an infinite number of points because it's a circle.
Yeah.
Okay, cool. Thank you.
Mhm.
For this system, would the friction be going like up the ramp if it's rolling down?
The friction is going up the ramp if it's rolling down.
Okay.
Now, the direction of the frictional force here is not meant to screw you, but the direction of the frictional force has to act to cause the correct angular acceleration. Always keep that in mind. Because that's where, if I wanted to trick you, I'm not sure I could, but I want to make sure you know that it's not about tricking you. It's about making sure you are thinking correctly about what it does. So imagine I roll a ball down here at the bottom, give it a velocity, and it's going to start rolling up this ramp now. So it's rolling up the ramp, right? Well, is it getting faster or getting slower as it rolls up that ramp?
Slower.
Probably slower, yeah. If there's nothing else powering it, it's getting slower. So what direction must the friction be in order for its rotational speed to slow down as it goes up the ramp?
Down the ramp.
No, up the ramp. The friction has to be up the ramp. It's got to oppose the direction of rotation to slow it down.
Oh, okay. Okay. I
It's
see.
already going up the ramp. So as an object which has kinetic energy here rolls up a ramp, it's slowing down. So the frictional force is up the ramp because it has to oppose the angular speed. Now, that seems counterintuitive until you realize that we have F times R acting down the ramp, or how about we just do it this way? Net force. F minus mg sine theta equals ma. Because F is up the ramp, mg sine theta is down the ramp. An object with rotational kinetic energy and translational kinetic energy will go higher up the ramp than one that just has translational kinetic energy. Why? Because it's got an extra force pushing it up the ramp. The frictional force is pushing it up the ramp, allowing it to claw its way up the ramp as it spins. But if you're concerned about the direction of friction, don't obey your gut here. If omega is up the ramp and it's slowing down, the frictional force is trying to stop that, to slow it to rest. Okay, Victoria, you're so kind to put your hand up on the little thingy thing.
Is it safe to say that friction is always up the ramp? Because I don't
No.
think we've seen one where it's down.
Would you like me to show you one where it's down?
Yes, please.
Fine. Let me dive into my bag of horrible physics questions that'll screw you over on the AP exam and see if I can come up with one. Don't make that face, Maddie. It could happen. Damien knows. Just look at him. He's ready. A lot of boxes there. Justin is so done with this night. I can just tell. Look, I'm okay. Whatever you guys are done. I've got my whole rock band set up. Right. Actually, you guys don't know this. I got drums for my birthday. So I've been playing drums every night. Like not rock band drums, like the real thing with like drumsticks and cymbals and the boom boom and the smash smash. Yeah. In my head, I'm a rock star, but I am so terrible. So terrible. I put my headphones on, I pipe in my music, and I play and I play and I play. And I realize at the end that I don't think I can hold a beat to save my life. Or to save your life. Like there's like a gun to my head and something and I just save my life. No, it's not gonna happen. All right, so let's find a way to make Victoria sad she asked this question. How do we feel about that? She probably had a nice night last night. We're going to take that all away from her right now. So here is like Mr. Shelton comes up with an AP exam question. And it's like, how bad do I want to screw over all of my students? This bad. Oh, could you imagine? Oh, I love it. So terrible, horrible, all at the same time. Look, I think Naomi just like flipped out a bit. Now, if you, let's say you had this on the exam, bail and go to the other two questions. But don't think of it too hard. It depends what they ask. Now, notice I connected the string to the axle of the thing that's on the ramp, which means the potential for it to roll. You guys see that, right? If the system is set up with a large enough mass hanging and the angle is small enough, or I'm sorry, big enough for this to work, small enough for this to work, then if the box falls, and that's an if the box falls, then mgh of the box has got to equal 1/2 mv squared of the box plus 1/2 big M v squared of the rolly thing plus 1/2 I omega squared of the rolly thing. No friction in sight. If I want to know how fast it's going, that will do it. And that's not a terrible question, right? It's no different if it was just a box. I just have this thing that is rolling, which suggests it will be going slower if it makes it to the top. But if it starts from rest, here's the thing. If it starts from rest, when it makes it to the top, it's got to be rolling this way, doesn't it? Which means the only way it rolls that way is if the frictional force acting down here is like this. But of course, would you all agree that it will be rolling slower than an object that slid up there without friction? Because some of the energy goes here. Is everybody okay with that? Well, if you're okay with that, then you realize the net force on the rolly thing has to be tension up the ramp minus mg sine theta, duh, minus friction. That friction only exists for an object that's rolling. I have to take away some of the potential acceleration because some of that acceleration is going into making the object spin. Is that okay? What is wrong with my face? Is there like a hole in my face?
It looks like your face is moldy.
It
I
totally
kind of thought you were
does.
just the Terminator, and we were just finally figuring out that you were.
Wow, that's awesome. I should totally leave it like that, but it's kind of freaking me out. You know why? I didn't change any of my settings.
Yeah, can you explain what you were going over again? Because your face kind of distracted me.
There we go. My face distracts a lot of people, but it's usually not for a positive thing. So, all right. So, again, if this was just a box that was being pulled up by a you know, that's not a box. This is a box, okay? And let's say for a moment there was no friction. It was just sliding up the ramp. Then there would be just this, right? And also there'd be just that. Now, if there was actual friction, then there would be minus work done by friction too. Right, if it was sliding against kinetic friction, then it would be slower because we would have friction slowing it down. Well, it's no different if it rolls. If it rolls though, the difference is that we don't lose that energy. that energy didn't go into heat spread out over the whole ramp. It went into creating another form of energy that the object keeps. But it does take away acceleration, preventing it from going as fast as it would if there was no friction. You see? But I needed to come up with an example of friction acting down the ramp, and I did. Also, imagine if you're riding a bike, Victoria. Have you ever ridden a bike? Or even a car. A car going uphill has to be able to push against the road upwards up the hill. That would be friction down the ramp, so that the third law of force is on the car up the ramp. It would try and dig in to push itself up the ramp. So a powered car spinning its wheels would attempt to push the road away underneath it, so that the third law of force would push the center of mass of the car up the ramp. That's harder to imagine, I think. Wow, that was a lot of torque stuff, Sana. Thank you. Feeling better about it?
Yeah, definitely.
I don't know if I am.
Mr. Shelton,
All
one
right.
more question before you move on. Wasn't there
Yes,
like a
Xavier.
threshold for like an object to be able to spin?
Well, yes, like anything that deals with static friction, we are still bound by the same threshold, which means that you need friction in order to spin, but you have a limited amount to get. So if more friction is required than can be provided by mu times the normal force, then you will not have enough friction to cause what you need to happen, which is rolling. So imagine you try to go up that hill in your car again. There is a minimum amount of friction necessary to continue to pull the car up the ramp without the tires breaking friction. If there's not enough of it available, then you will be unsuccessful at going up the hill and you'll slide back down. So yes, there is that. And in all of these cases, although we can't necessarily say these are equal, if they ask for a threshold problem, what is a max, what is a min? Ask yourself if this is what they're talking about. Under those circumstances, the maximum frictional force can be replaced with mu times the normal force. And under that circumstance, you could then plug those in and solve for what the threshold is. Generally, you're maximizing something here. Maximum angle, maximum value for mu, minimum value for mu. Does that make sense? Just be aware though, whatever you're plugging in there, it is likely that you are solving for one of these two things. So if it's mu, that's easy. If it's n is probably going to be based on some angle thing. Probably, if it's an incline. If it's not, then it's based on how much weight you're putting on the object. People used to fill the bumper of the bed of their truck with rocks to give them more friction during the times when it's slick roads. You know, in places like Arizona, you know, because everybody owns a freaking pickup truck there. All right. Don't fail me now. What do we got? Come on. Wow, we haven't even touched one E&M thing yet, but SHM review and momentum, angular, and linear. Who wanted SHM review?
Mr. Shelton, I have a quick question first about that last problem. If it was being pushed up the ramp from behind, would the friction still be down the ramp? Or
Like I'm standing
yeah,
here
like if there
pushing
wasn't
it.
like if instead of a rope pulling it up, if there was someone behind it pushing it up, would it still
Look,
be down
if
the
the
ramp?
angular speed is increasing in a clockwise manner, there must be a clockwise torque acting on it.
Okay.
So if I'm grabbing this handle in the middle of the wheel where I can't apply a torque, so I'm holding this and I'm pushing it up the ramp, the only way the wheel's velocity increases in a clockwise direction is if the frictional torque is clockwise. Period. Don't try and get away from that. If you want something to change its velocity, it takes a torque, and a torque has to be in the direction of the change. End of story. Okay? Could be aliens pulling on it in this direction. It's going to roll up the ramp, and its angular speed is going to change in a clockwise direction. There has to be a clockwise torque. If the only point of contact is a frictional force at the edge, that's it. Don't make it harder.
Oh, right. Because if the friction was going the other way, it would just roll the other way, and you wouldn't go.
It would roll the other way. That's right. The aliens were unsuccessful, and it steamrolled me. Done.
Yeah.
I can stop talking about physics on a Saturday night. But it's only 7:30. A lot of Saturday night left.
Thanks.
So I can go back to my list. I can cross this, and I can cross that, and this, and this, and okay. Who wanted this? Who was this? Who said it?
That was us.
What do you want me to say? What do you need to hear? What's the skinny there?
Can we go over more distinctions between what to do differently between actual a spring oscillating, a lot of those questions, and circular motion?
So you want me to try and tell you how the taste of grapes is compared to the feel of fabric?
Yeah.
All right. I'm going to do my best here, but basically you asked me a question like, what is physics? And I'm supposed to reply. So I don't even know where to begin with your question. It's like you just picked two random things and said, tell me how they're different
Overall,
and how
I
they're
just
the
want
same.
I just want more review of simple harmonic motion.
All right. So give me a second.
Well, I have a specific.
No. I've disappeared. Have you noticed? Mr. Shelton has left the chat.
Oh,
He's gone.
okay.
Okay. Finished my Dr. Pepper.
Diet Dr.
Oh.
Pepper. Grape soda.
Yes. It's just such a big question, and in order for me to tackle it, I don't have a premise. So or even idea in mind of where to begin. How about we go old school? Here's an old school question. You might not remember this question from a long time ago, but I do. I'm going to drop a box on a spring. Now, do you remember that there's a variety of questions about energy related to this problem? Do you all remember that? Now, in dropping the box on the spring, all things considered and no external forces, the box will make it back to where it started. By definition, if it's an ideal spring, and there's no way for energy to leave the system, the box will strike the spring, compress the spring, and then the spring will recoil back to its original shape, pushing the box back upwards, and the box will return here. All good? Now, there's a lot of ways for us to deal with that, and a lot of little tiny interesting questions in the middle of that. Like, what's the maximum speed of the box? First, that is not the speed that the box reaches when it falls a distance d. The box continues to accelerate downwards even after it hits the spring. And the reason is because when it first makes it to the spring, currently the net force on the box is still mg. The spring hasn't been compressed. And since the upward force from the spring is based on how much the spring is compressed, if x equals 0, F equals 0. So at this instant, the net force is still downwards, and therefore the box is still accelerating downwards. After a few moments, the spring has been compressed some distance. It will eventually make it to a point where mg equals kx, where this distance from here to here is kind of lost space, but we'll say x. Let's make it so that we have a distinction. So we'll say, I need another color, we'll use red. So from here to here, and we're going to call that x0, so that we know this is the moment we've reached equilibrium. Good so far? Equilibrium. That's the maximum velocity. Because now net force is 0. We've reached a point where the upward force is balanced by the downward force. So we've got to the point where we are traveling fastest. Basically, mgh is going to equal 1/2 mv squared plus 1/2 kx naught squared. Now, if the box sticks to the spring, it will engage in simple harmonic motion. But we don't know what the amplitude is yet, because the box hasn't come to rest yet. We have determined where the equilibrium position is, but the box still has velocity, so it's going to continue to compress the spring until all of the energy has been converted into elastic potential. So the box makes it to here. Finally comes to rest, and the spring has been compressed a distance that I will call A, amplitude. Now, this really isn't the amplitude, so let's not call that A, because amplitude would be from here to here. So let's call that A plus x naught. The distance from the unstretched length of the spring to where it finally comes to rest. That means mg plus dx naught and A. That's how high it started here. This is where it ended here. That was the total amount of potential energy relative to the lowest point it attains, has to equal 1/2 k x naught plus A squared. Now, somewhere in the middle of this, since Josh asked for a simple harmonic motion question, they're going to say, what is the period of oscillation? Because that's generally what they do in these stupid questions. They tack on a simple harmonic motions part right at the end. With all of this distraction, you're probably thinking, what the hell do they want? Don't be confused. period has nothing to do with energy or amplitude. Period of oscillation is a factor of the restoring force and the inertia, always. Simple harmonic motion is really about cutting away issues of amplitude and issues of max velocity and all that garbage, and recognizing that the oscillations are independent of the amplitude and are only based on physical parameters of the system, things about inertia and about restoring force. However, Victoria has the sense to say she doesn't want to interrupt, so she throws her little hand up there and hopes that I see it in her little box, and I didn't. So I'm staring at Josh's little box where he is not socially distanced from Ryan, and they both look like they're in a cave somewhere. So get out in the sun, you guys. I know Ryan's out in the sun. He runs a lot-ish when he's not playing guitar and singing. So Victoria, what?
What was the thing about period that you wanted us to memorize? Was it like 1/4 T or 1/2 T when things were equal? Like you were going over simple harmonic motion, you were like, memorize this. Or like they might ask you something about this and it's like 1/4 T or something.
Okay, well, let me make my point and finish my point. Then I'm happy to go to your point. Okay? Say okay. Let me know I don't have to look.
Okay.
All right, so what I want to point out to Josh, that this is a problem. This problem has been on the exam. And it has been on the exam since the 80s, which I would say, warning, Will Robinson, has been on the exam since the 80s. Why not put it on the exam this year? Why? Because no one's ever seen it in years. And we've done this problem. And there are 3 important details I hope you wrote down. The first, I see lots of potential lowest points in the problem, right? All situational. The potential energy to figure out the velocity when it just hits the spring is based on a reference level of D. A reference level when it makes it to the maximum velocity, when the net force is 0. And a new reference level when it makes it to its actual lowest position, when all the energy is finally elastic. I've reset the reference level 3 times to serve my needs. Be willing to reset the reference level to serve your needs. Next, maximum velocity is always attained when net force is 0 for all oscillators. Hang a box on a spring, that's still true. Slide a box against a table, still true. A pendulum, lowest position, net force is 0, because even in a pendulum, the force is mg. Net force is 0 when the pendulum is back to center, tension and weight, not balanced, but there's no force in either direction, this way or this way. There's no restoring force. That's when the velocity is fastest. We're at our lowest position. Now, that being said, an oscillator questions remind us that there's the basic idea of an oscillator, that we have these functions for period that are related based on physical parameters of the system. All of them basically the same, that we're talking about inertia over restoring force. Nothing about amplitude or energy. The oscillatory properties, the fact that these are timepieces that do their repetitive motion over and over and over again, have nothing to do with how much energy you put in the system or the amplitude of the system. But the truth is, the amplitude and the energy are what's connected together. Those are the things that are linked. The more amplitude I have in my system, the more energy I have in my system, but none of that affects the period. Now, that being said, keep in mind that there's other things at play here, and that brings up the question that Victoria is asking, like, what are some things I should know about like parts of the period? Well, it's nothing specific. It's the idea that if you have an oscillator, a block attached to a spring, if the block, let me do this different. If it's just a block heading towards a spring, well, look, don't think oscillations for a minute. The block is going to slide across the ground, hit the spring, slow down till it compresses the spring, stops, then be pushed back, right? Well, it's not really an oscillator. It hit a spring and got pushed back. But from the moment it touches the spring till the moment it is not in contact with the spring, for that time period, it is a spring mass oscillator. So how much of an oscillation does it do? Well, it compressed the spring from equilibrium to maximum compression. That was 1/4 of a period. It returned to equilibrium. That's another 1/4 of a period. So if it didn't stay attached to the spring, it was only attached to the spring for half of a period. Now, if this was all sticky and it stuck to the spring, then it would come out this way and stop when it stretched the spring out, another 1/4 of a period, and then would be pulled back to center, the last 1/4 of its period. Follow that, Victoria? Now, could you use that? Sure. It is the only way to answer the question, how long does it take the block to come to rest? Because you can't use any motion equation because the force here is changing as the block compresses the spring. The only thing you can use is something related directly to simple harmonic motion, because that motion equation we can use, but you really don't want to have to use this motion equation. You want to use the fact that you know you're dealing with 1/4 of the period. But you could. I mean, if you think about it, and I'm really just talking to Victoria at this moment, and I hope she's really listening. You could use the motion equation to figure out the time, because you're looking for the time in which x equals a. So, but just do quarters here. Just do quarters here. You'll be happiest. Now, unfortunately for all of you, Mr. Shelton just thought of something. I know, Xavier, that's bad news. You do understand that we never really talked about the energy here. I mean, yeah, I know. MGL1 minus cosine theta. We did that whole thing where I told you to take the derivative, and we showed that the energy is rotating just like anything else. But at its equilibrium position here, all the energy is in kinetic, right? The net force isn't 0 here. Unlike the spring mass oscillator, the net force isn't 0, because at the very bottom and everywhere in between, except for when it stopped, everywhere in between, except for when it stopped, net force has to equal MAC, which means at the very bottom, the tension has to be greater than the weight so that it still stays in circular motion. Don't flip out at that, Just understand, the restoring force is about returning it back to center. So in this case, the net force in the x direction is 0. But the net force in the y direction is that. And considering that you can figure out the velocity, means that you could figure out the tension in the rope for a simple harmonic oscillator. That is not true when it stopped. When it stopped, the tension in the rope is going to be T cos theta equals mg. So the tension in the rope is mg cos theta. I just did, the fancy math of putting one of those on there and one of these on here and all that crap, garbage stuff. I'm sorry, I'm recording this. All that stuff, all that wonderful physics garbage. But remember, this is the tension when it's stopped, because net force is 0. Actually, no, I just lied to you. It's stopped, but net force isn't 0. It's 0 in the y direction, but there's a force that way that's trying to make it go back. But that's still the tension in the string. But I don't think they're going to go with that. I think they're going to go with, if they're going to ask it, they'll go with something like that. Why? Because it's a good oscillator question. And it's important to understand that because it's a pendulum, it's in circular motion. Wow. All right, I'm getting a little punchy here. So we've been going for a solid, 2 hours, 2 hours and 20 minutes. I was hoping my batteries would run out by now and I'd have to turn off. How about we say Hail Mary, and is there really anything else we have to talk about? I mean, we haven't talked about anything with E&M. Poor E&M kids. They're screwed. We should have another one of these tonight just for E&M. And if you guys, look, I don't want to do this. There's something in it. Who posted in the chat? I have to go. Thank you, Mr. Sheldon. Oh, you're welcome, whoever that was. Look, E&M folks in the chat, send me a private message. I will do this tomorrow night if you would like. It would have to be at 6 o'clock or later. If you want to show, just say yes. If you're not going to show, you're not interested, just say no, but just give me a message there. I think I should show you something else real quick, just as a quick 2-minute. Are you prepared for something that we talked about first semester and I never brought up again? And it's not that I have a hunch, I don't. It's just one of those things that we didn't do anything about it in the review. And I feel bad that if it came up, you would be blindsided. Okay, you see it? Do you realize that if cart 1 hits cart 2, that there will be a moment when cart 1 and cart 2 are traveling at the same speed before the spring pushes them apart again? That's the answer to the question, what is the maximum compression of the spring? It has shown up on the exams very infrequently, but I feel like it's one of those questions that could make a resurface, because this is a perfectly elastic collision if we assume an ideal spring and no friction on the ground or in the system. And when this problem comes up, students lose their mind and the average number of points is like 3. But in this problem, the maximum compression of the spring occurs when both cars have the same velocity. Because before that, this car is still moving forward and pushing into the spring. And then they have the same velocity, and then this car starts to slow down and the other car starts to speed up, and they no longer have the same velocity. They only have the same velocity when when the spring is at its maximum compression. So you do the elastic collision I'm sorry, the inelastic collision first to figure out what velocity the cars have to have for them to be at the same velocity for that instant. Then, and here's the juice. The original kinetic energy was that. The new kinetic energy is that. But now there's energy in the spring. That's how you figure out how much the spring was compressed when that happens. Now, let's see if I can do something real quick. Whee! A couple years ago, a ramp that can slide across the ground with no friction. And a box that can slide up the ramp. Exact same problem in that this has MV. How high does the block slide up on the ramp? Well, this was the kinetic energy before. This is the kinetic energy now. And now there's for how high the block slides up on the ramp when they're both traveling the same speed. It's one of those silly little things, but if they make it the focus of an FRQ, gee, I'd hate to not bring that up because somebody asked about collisions. And this is one of those weird collisions. Do I really think it's going to happen? No, Riley, I don't. But I want to cover all the bases. You guys have been hanging out for a while. That seems like all the bases. Now, put your pencils down for a minute. Let me turn this